Alright, in this third review slide, we're going to look at an application of what we've already been doing, 1D steady state conduction. So we're going to start with the Cartesian form of Fourier's law, written as Q equals minus Ka dt dx. And of course, what we've been discussing is that this is the term that we need to be able to evaluate. So we've just utilized the heat equation to develop a methodology for finding what the temperature field is. And we'll start here. So here is the expression of the 1D Cartesian heat equation, and it is, we recognize it as being a second order ordinary differential equation, and because it's second order, it implies that there's going to be two unknown constants which we're going to need to solve for by specifying two boundary conditions. So the quantity in the parenthesis up here, since we're taking a derivative of some quantity and it equals 0, the quantity inside the parenthesis has to be a constant, and we can take that, separating variables and integrating both sides to give us an expression for temperature as a function of x in terms of these two unknown constants. We can solve for these constants by specifying the temperature at x equaling 0 and at x equaling L, calling them just T1 and T2. We go ahead and utilize these values, these two boundary conditions, putting them back into our general form of the solution for the second order ordinary differential equation. We get that the first constant equals T1, and then utilizing the second boundary condition, we find out that C1 equals T2 minus T1 over L. And this gives us our particular solution to the ordinary differential equation for these two boundary conditions. And we get temperature as a function of x. Here we're going to have a constant slope for, so again, it's equation of a straight line, right? Just like y equals mx plus b. In this case, the slope is given by the change in the endpoint temperatures divided by the thickness of whatever material we're going through. Now that we have this temperature as a function of x, we have the ability to take the derivative of it with respect to x. In this case, it works out to a relatively simple value, again, T2 minus T1 over L, which, as we expect, is a constant. We're going to take that value, and now we can utilize it in Fourier's law and give us an expression that we can evaluate. So Fourier's law for this particular 1D steady state conduction in Cartesian form equals minus Ka T2 minus T1 over L. And again, remember that T1 is at x equaling 0 and T2 is at x equaling L. So we can start here, and also we want to talk about the particular form that we're going to end up with is that we're going to try to utilize this concept of thermal resistance, and the way we get there is from this electrical analogy. So voltage equals current times resistance, or for our particular case, we're going to want to look at it as current equals voltage over resistance, and the analogy is, as current flows in electrical system, we have heat flowing in our thermal system. It's being driven by this temperature differential, and we have thermal resistance that's going to resist the temperature flow. And the thermal resistance is going to be given by the total width or length that the heat has to travel through, divided by the thermal conductivity rather, and divided by the area. And the area is just going to be the area of the material that the temperature is then passing through. Alright, if we want to, we can now look at a quick example. So again, we're going to have a typical slab of material. So again, the direction that the heat is traveling is in this direction, from an x equaling 0 to an x equaling L, and then we just have an area of the slab. And again, this area is sometimes considered rather arbitrary. We could divide through by the area and just provide our answer in terms of a heat flux. And in this particular slab, the left-hand side at x equaling 0, we have temperature T1, and at x equaling L, we have temperature T2. Now to go ahead and evaluate this type of problem, we need values for these specific quantities. And once we have them, we can go ahead and evaluate. Now again, to utilize Fourier's law, we need to calculate this quantity T2 minus T1, where again T2 is at x equaling L, T1 is at x equaling 0, and this evaluates to a minus 50 degrees. My thermal resistance is going to evaluate, again it's L divided by K over A, and this evaluates to a numerical form of 0.014 Kelvin per watt. So now I can take these two particular numerical values and take them and put them back into the form of Fourier's law that we're working with. And we see that the negative signs, keeping them, maintaining them where they're supposed to be, shall we say, we end up with a positive value for Q of 3600 watts. And again, the positive value indicates the flow of heat is from T1 toward T2. So T1 is 100 degrees, T2 is 50 degrees, and as we expect, the heat flows this way from left to right. Now again, remember that T1 is associated with x equaling 0, and T2 is associated with x equaling 1. So the heat is flowing in the positive direction, and it happens to be, again, downhill. So this is our quick example of the 1D steady state conduction in Cartesian form.